Just to give a brief intro, Professor Rama received her undergraduate degree in 1984 from IIT Delhi and her PhD in 1994 from Indian Institute of Science, Bangalore. She has been a postdoctoral fellow at Caltech. She has worked as a scientist in National Aerospace Laboratories in Bangalore. Before joining ICTS, she was a faculty member at JNCSR, Jawaharlal Nehru Center for Advanced Scientific Research in Bangalore for 14 years. And since July 2012, she has been associated with TIFR, first in Hyderabad and then in Bangalore ICTS. The topic of her talk is related to cloud computation. So her research group has been actively involved with clouds and formation of clouds and formation of rains from clouds and the dynamics of raindrops and so on. She also works on turbulent flows and so on. So that's about Professor Rama Govindarajan.
Okay, so before we go into clouds, I'm just putting up these pictures of other dusty flows which are in the environment, which also need AI ML methods to solve them really. And they are very, very connected to cloud computation. So if you can compute clouds, like you can compute many of these other dusty flows, keep that in mind. This is just a picture of what clouds look like over a year, like it's a daily average or something shown, and you see how India gets covered in clouds during the monsoon. So there's lots and lots of open questions about cloud. They're going to affect climate in a way we don't know. We don't know whether clouds will increase or decrease. We don't know anything. But today's talk is about which cloud will rain. We're not going to talk about all those details. We're just going to ask, if I'm given a cloud, can I say whether it rains or not? The answer is no. So we will just see how to proceed in that direction. Okay, what's a cloud? There's water vapor which evaporates in these blobs from the ocean and from other wet regions of the earth. And then because it's warmer than the surroundings, it's just evaporated, and it's lighter because of water vapor content, it rises through the atmosphere. As it rises through the atmosphere, the temperature decreases in the atmosphere. You know that, right? Like as you go up in the atmosphere, the temperature is lower and lower. So it encounters lower and lower temperature, and the relative humidity therefore goes up, up and up. The water vapor that it's carrying becomes more and more humid in comparison to the local temperature, until it reaches a line called the lifting condensation level, which is unique for each cloud, depending on how much it's carrying. And above that, these aerosol particles in the atmosphere, they act as condensation nuclei, and little droplets start forming on those condensation nuclei. So like you have a cloud above a line called the lifting condensation level, right? Now, why this problem is hard? We'll first talk about why it's hard and then why it's interesting. So we are solving the Navier-Stokes equations plus many other things. So here is the Navier-Stokes. U is the flow velocity in the air and P is the pressure. R is the Reynolds number. How many of you don't know Reynolds number? Okay, great. So somebody lifted their hand. Okay, great. So like these clouds are at extremely high Reynolds number, and there is forcing on the Navier-Stokes due to the water vapor, due to temperature, liquid water, dust particles. We'll come to all that. And remember, this kind of thing applies to more things than the cloud. The Reynolds number in the flow is very, very high, like million, 10 million, that kind of number. The Reynolds number relative to each particle or each raindrop could be from 0 to 10,000. So this is the kind of thing we're contending with. Okay, and then there are further complications. First of all, in the previous talk, did you all notice what's the resolution that these models are running at? How much? What? 25 is typical. What was the smallest? 10, around 10. He showed one thing which had something like 3, but like 10 kilometers is like here to MS Palya, okay? And what we need is a resolution of 1 micron. So like to understand the physics, this is what we need. So we absolutely don't have that. This distance between the highest scale in the problem and the lowest scale is a mind-boggling 13 orders of magnitude, which no computer can do. So we have to think of other ways. So length scale itself is a major problem. Then what are all the complications involved? There's aerosols, which act as cloud condensation nuclei. There's raindrop growth in the presence of turbulence, and blah, 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 and lots of other physics coming in. And you have in every CC is like this much, okay? You have 1,000 droplets in a cloud, 1,000 inside every CC. So like these all are interacting, doing things. So that's the whole problem. And we can write some very simple equations connected to phase change. So like here is Navier-Stokes, and we have forcing only from the light, the fact that when temperature becomes higher, you get lighter air. So as temperature increases, there's lighter air, and as temperature increases, it's heavier. So you get differences in density in the flow, and this becomes differences in buoyancy, which could make things rotate, which could make things rise and fall, things like that. So buoyancy is a very, very important thing. And then temperature equation, water vapor balance equation, and then for each droplet, we have to write a series of equations. And however much water vapor condenses, that much latent heat is released, and that goes as a source term in the temperature equation. And the temperature determines the buoyancy, because the buoyancy is related to temperature, water vapor, liquid water, everything. Okay, so you see how these equations are tied up to each other. And for each droplet, you have to write, I mean, the simplest thing you can do is write a Maxey-Riley equation, which tells you how the droplet follows the flow. And this thing is a Stokes number, which is like a reaction time of the droplet. And then each droplet is growing in radius as well. So its Stokes number is changing with time as well. So all of these go into the system. And this is all at the tiny scale. Got it? Now, as we discussed, proper numerics for 10 to the 13 orders of magnitude is totally not happening, which is why we need AI, okay? We need cleverer ways of doing this thing. It's totally not happening. And in climate models, I wrote grids of 10 or 100 kilometer size. That's the kind of thing that climate models do. And what we need is to go to each micron. So inside, so usually like flow scales are taken as 1 millimeter, because if you take normal turbulence, then all the physics happens at 1 millimeter or half a millimeter and above in clouds. So like if you're just doing turbulence in a cloud, you can have a grid which is something like half a millimeter or 1 millimeter. So that's the flow scale grid. But inside each grid, there are all these 10 micron droplets in a cloud. I told you 1 cc has 1,000. So these are the 10 micron droplets in a cloud. And if you really want to do it right, you have to resolve each droplet with a grid around it. So you have to have a complicated grid like this around each of these droplets, and then connect the answers from here to here. Only then you will get the correct answers. And now, like to give you an idea, today's biggest simulation is this much cube. And if you want to go to 1 millimeter size, how much is this? How big is this domain? It's like 16 meters, right? 16 meters, correct? So you can only solve, like in the world's biggest computer, 16 meters of a cloud. So which is so much smaller than 1 kilometer or 10 kilometers. Yeah. And then like there are people who do just this with just turbulence. This is the biggest. And then there are people who do just particles without like big scale in turbulence. And those guys can at max, the record in the world is like lakhs of particles. And lakhs of particles will be contained in this much area. Lakhs of, I mean, I'm using droplets and particles as interchangeable. Okay, it will only be contained in this much area. So we cannot solve for each particle. And why is this not okay? This is not okay because the whole system, Earth system, is non-linear, right? And non-linear means every scale forces every other scale. So if I'm taking a 10 kilometer scale, it will be forced by the smaller scales. So I can't just pretend that 10 kilometers is the smallest scale. Similarly, these scales will be affected by the big scale. So I can't pretend that I know what the big scales are doing. So whenever we divorce these two from each other and solve small scale separately, big scale separately, we're doing a gross assumption where we are, truncating all the Fourier components above a certain thing or below a certain thing and saying they don't force, but they do force. And then what we do is we parameterize. So we try to say, okay, these small scales are going to do this much only, and we'll put that as 1 or 2 numbers in our big Earth simulation. And that can go very wrong. And in clouds, we know it goes very wrong. So this is the whole thing that we need to incorporate theoretical understanding, normal I and AI, and all of the above. Okay, so what does turbulence look like? This is what turbulence looks like, where they've colored the vorticity. So how many of you have seen something about turbulence before? A few of you. So the basic point is that, okay, I'm standing here, right? Above my head, there's a turbulent plume because I'm warmer than the atmosphere. I'm actually an engine which is messing up the world and warming up the world. So technically, I shouldn't exist. But yeah, like there is a turbulent cloud above me, if you could see it. So because I'm warmer, there's a buoyant plume which is rising. So almost any flow on Earth is turbulent. Okay, and in this room, because of AC, we'll have turbulence. We don't see it. So everywhere, anything biggish is turbulent. And we'll think of turbulence today as consisting of vortices. And vortices are just regions. In this region, the del cross U is high, that's all. Del cross U is high. That's all you need to remember. And it's basically a circulating region. So I have these noodle-shaped things which are all circulating, rotating very, very fast. So these are my vortices. And in my vortices, you need to remember that this is the vorticity, the del cross U that I told you. And this is the symmetric part of the velocity gradient tensor. And we have a quantity called Q, which we need to remember for this talk. That Q, when it's positive, then it's vorticity dominated. When it's negative, it's strain dominated. So in all these green regions, its Q is greater than 0. And in all the black regions, Q is less than 0, broadly. Okay, so in these regions, so these are like rod-like things which they are born, they die, they move each other around, they twist each other around, they knot up, they unknot. So vorticity is doing a lot of dramatic things in turbulence. And then they are the leaders, they are the winners of what they do to particles. So that's why we need to know about them. Where did I put my... Oh, I've left it there. Yeah, this will happen to me several times in the talk. Okay, so now let's think of droplet growth. We are asking which cloud will rain, right? Let's not lose sight of that. So how do droplets grow? So in a cloud, they can reach about 10 micron size just because the surroundings are supersaturated. But beyond that, to grow, it's very, very, very slow by just accreting the water vapor from the atmosphere. And suppose they're very big, like already 100 micron in size, the big 100 micron guy can fall through the small ones and collect them, coalesce with them and grow very fast due to gravity. So gravity acts after this pink line and diffusion acts before this pink line, this other pink line. And in the middle, we don't know what's happening and how they're growing from 10 micron to 100 micron. Any calculation we do, like back of the envelope calculation, we will get that they'll need many days to grow. And clouds don't have many days. It reaches from 10 micron to rainfall in half an hour. So how does it grow? That's called the droplet growth bottleneck. It's not a completely answered question. So there's a question mark over there. Then we talked about why this problem is hard. We all agree that the problem is hard. It cannot be solved very easily on any computer. We need methods, we need to think out of the box to actually solve it. And we'll also talk about why this problem is special. It's very special because at small scale, multiple physics stuff is happening. Different things are happening at small scales. These are all affecting the big scale. And usually we are blind to all this and we put parameterization, which doesn't work too great. We know that it doesn't work too great. If I make a parameterization which works very well in a certain part of the world, let's say Germany or something during a certain part of the year, it's absolutely not going to work for us in India, and we are not able to predict like rain or any such thing. So let alone after climate changes. Right now itself, we're not doing a great job. So like this is very, very important. We'll talk about some of these things. So first of all, like, you know, when you put like sugar in our tea, we think of turbulence as a good mixing agent, which makes everything uniform. So suppose I start with sugar at the bottom and tea on top, I mix with a spoon and sugar goes everywhere into equal concentration. And then I can sip my tea. But see what it does to particles. So these are droplets in a cloud, you can imagine, and see what happens. So they're all uniformly mixed in the beginning, but then they get thrown out of certain regions, and these are the vertical regions. These are the regions which are, you know, those noodle guys, if we cut them. You got that, right? So those regions, they don't contain particles. So particles centrifuge out of those rotational regions where Q is greater than 0. So like you have this kind of centrifuging, and you can do some back of the envelope calculation, and you can convince yourself that for rain to form, like if you forget this whole talk, just remember this one thing when you go home or when you go back and think about what lectures you attended today. Just remember that you need powerful, very, very fast rotating, strong, tiny vortices which can, out of which these 10 micron droplets will come out, centrifuge out. And that's going to be an important mechanism for rain formation. So you need more and more powerful small vortices. And one thing to tell you is that, you know, as you go up and up and up in scale, like suppose you're looking at 100-meter setup, there the tiny vortices will be way more than in a dabba of this size. Like in my washing machine, I'll never get those tiny vortices. But in a cloud, I'll get way more tiny vortices. And when I'm simulating small scales, I can't go there. So I'm doing in my washing machine or some dabba, and that thing will not contain the small vortices, so as many small vortices. So we have to do extrapolation and thinking and AI to account for how much raindrops will grow. So this is a question. So, and all the droplets themselves are cloud condensation nuclei. So when the droplets move out of the vertical region, and suppose everybody became a droplet already, then you cannot have condensation inside the clouds, inside the vortices, because you need droplets to make to grow and have condensation. Any questions of clarification so far? We don't, but in IIT Madras, there is one, certain places have. Yeah. So those general questions keep for the end. Just if I'm not clear on something, ask it now. We'll see that. What? Advection. Yeah, there's lots of things. Like advection is part of the solution of the Navier-Stokes. Turbulence. Yeah, and yeah, you're right. Like large-scale advection is a separate thing. No. This is not, I mean, this is just a contention that I'm making. It's not any proof for it. Okay. So how do cloud droplets talk with turbulence? We've seen that turbulence and cloud droplet interaction is needed to bridge some of this bottleneck, right? To go from, you know, some months to form rain to half an hour to form rain. So reality says in half an hour you get rain, and in any estimates you get rain after months. And we know that no cloud will live for months. If I come back after some 15 minutes, I'll see a different cloud pattern. So clouds last like hour or even less. So there are two stories which are connected to each other, and mainly I want to talk about this story today, and I'll talk less about that story. So there is turbulence. Turbulence achieves centrifugation, which we saw in the last movie. And wherever the droplets are, there's going to be condensation. So because of centrifugation, there'll be condensation outside the vortices. because droplets are now outside the vortices if they go out fast enough. If the time scales are suitable for us, then you'll get condensation only outside the vortices, and therefore you'll have temperature inhomogeneity, because wherever you get condensation, you get latent heat release, right? So that part becomes warmer. So will the vortices be warmer or colder by this argument? Colder. Yeah? No, what? Of course, everybody has a temperature, right? There's a temperature in every part of the atmosphere. Yeah. Colder. Why do you say that? Yes. Yes. So like suppose I have a vortex here. Suppose I have a vortex here and the droplets are all outside. Then there'll be growth outside and latent heat will be released outside. So the outside will get warmer and the vortices will remain colder. So we are going to have cold vortices. Everybody got that? Yeah. So then now we have this temperature inhomogeneity. So temperature is not the same everywhere. And initially I told you, like if there's a lighter patch here, then a heavier patch here. So this is warmer and colder. Warmer means lighter, colder means heavier. You have these two patches side by side, you're going to have baroclinic torque. So you're going to have rotational motion. So you're going to have turbulence and small vortices being created. So anytime I have a small temperature jump, I'm going to have small vorticity being created. So like we earlier talked that we need small vortices to have rainfall. And now the droplets are themselves creating the more small vortices. So they're actually feeding back into the cloud. You're getting this? That's the model I want to convey today. And so like you have more small scale, more collisions, more coalescence, stronger turbulence and everything. So this is the story that we are going to talk about. And you can see that in picture here, like here the droplets are all outside the vortex. This green thing is the vortex which is rotating like that. And those droplets are growing. And because those droplets are growing, the surroundings are getting warm. And because the surroundings are getting warm, you're getting baroclinic torque at the edges. Cool? Okay, so like now this story of centrifugation alone is not enough for making droplets. Droplets have to come closer together and then they have to collide and coalesce to make big raindrops. Like you have only this mechanism after 10 micron, like they have to come together and coalesce. So how big is a raindrop? Order of magnitude? Micrometer, you don't see raindrops. Huh? Millimeter, around a millimeter. So let's say 1 millimeter. And I said the cloud droplets, they grow till 10 micron without collision. How many collisions should happen and how many coalescences before it becomes 1 millimeter? Can you estimate it? 10 micron to 1 millimeter. What? How 100? 10 micron. How many 10 micron droplets need to join to make 1 millimeter raindrop? 5,000. Yeah. Yeah, 1 millimeter is 10 to the power minus 3 and 10 micron is 10 to the power minus 5. That's the radius. We're talking volume. 1 million. It's a factor of 100 from 10 to the minus 5 to minus 3, and 1 million have to come together because volume is radius to the power 3. Correct? So for 1 million coalescences, you'll need something like 50 million collisions, because not every collision results in a coalescence. You can have droplet breakup because two came and dashed and spoiled all the work for you. So in order to make one raindrop, you need 50 million collisions. That's the kind of like number we're talking about, maybe much more than 50 million also. So this is the story. So like you need a lot of collisions. which can never ever happen if you do like just random walk, if the droplets are just doing random walk. So you need a better understanding of how they cluster. So one thing is they leave the vertical region, they cluster in the strained region, but that also is not at all enough. They have to cluster much, much more. So there are many mechanisms for clustering which we keep studying. Like why do they come so near each other? And that's a very nice AI question, because once we know the physics, we can actually estimate it using AI. And then like coalescence, collisions to coalescence is a big question mark. How breakups occur, how things happen, that itself is an open area of research. The centrifugation, we talked a little bit on the back effect on cloud. We'll talk more about it. And here Rajeshi has done a simple simulation where he has a few lucky drops, few guys who are already big, very few, and like a sea of small droplets, 10 micron droplets. So suppose in a cloud, magically I'm putting a few drops who became already big by some luck. Then how they eat the rest of the drops. So like these things get centrifuged very fast and they're eating the whole vortex of small droplets and they're growing as they go out. So they get centrifuged out faster, so they eat more small droplets. So this is a kind of, you know, thing which increases collisions if you have a slight heterogeneity in size. So this is one kind of aspect we can study. I won't say more about that today. And then there is this back effect we'll talk in some detail. And these things we'll mention in the end if we have time, like how interparticle interactions increase clustering, like each droplet knows the other droplet is there and clusters therefore, and how gravitational settling, that we'll not talk about today. So the back effect on cloud due to condensation. The first part of this work was conducted in collaboration with S. Ravichandran, who is now in IIT Bombay. He's a faculty member in the climate department there. And Nikita and Bipin, they are in IITM Pune. Hopefully they are in the audience, or at least I saw Bipin in the audience a while ago. He's among the organizers. And Yogesh, who was a postdoc here, he started this work and he did work on it for quite some time. And after he left ICTS, unfortunately, he passed away. So I'd like to dedicate all these findings to his memory. So, yeah. What is the back effect on clouds due to condensation? We talked about droplets going out. I'm just going to show you a movie of everything we talked about. These are all vorticity. These are all positive and negative vortices. So they're going this way or that way. For droplets, it doesn't matter which direction they're going in. So the droplets are going to get centrifuged out. And because of that, they'll condense outside and the temperature will be hotter outside and you'll get cold vortices. And because the condensation is happening outside, the outside will dry out. Water vapor will be sucked away. Whereas in the vortices, the water vapor will remain. So the vortices are going to remain wet and cold. And then the liquid water is going to get created outside the vortices. So you just see a simulation of that. It's not very exact, like, liquid water takes different shapes. It gets centrifuged out even more and so on. But you get broadly the idea of what I was saying. So these are cold vortices which are wet, and then you have liquid outside. You have more droplets forming outside. And this is just like now we're coming even down in scale and we're asking like what other physics is happening and why is all these changes happening because of these droplets centrifuging out. So like suppose, there's a toy model of just two vortices. So if I left two vortices just like that, one going this way, one going this way, and they're now not in turbulence, they're the middle of nowhere. So just imagine two long noodles and they will just go down because of it's effectively Biot-Savart law. They will interact on each other to push each other down. So this is all that they'll be doing if they're some normal vortices which are not cold. Now let's see what happens to cold vortices. The same two, and here there's vorticity and here there's temperature. So they're colder than everybody and now they're starting. And now instead of going passively down, they do something very different because buoyancy is playing a role and Magnus lift and many physics things are happening, even in this, just a pair of two vortices. So this is just to drive home the point that cloud turbulence is different from normal turbulence. cloud turbulence is going to be very different from normal turbulence. You started with 2 vortices and it's now become many. It's just periodic, so it'll keep jumping. Sorry about that. Bad movie. So like now you started with 2 vortices, but you still see that the vorticity is cold. Inside the vortex, you still got temperature which is cooler. And you see what a mess it's created and so many small scales. And this is what is going to happen when there are 2 cold vortices. Just one indication of what will happen. And this is just an estimate to say that all of this will not happen if the condensation is too fast. So it depends on centrifugation versus condensation. So those time scales matter. That's all that this is telling you. And now we talked about just 2 vortices going up and down. And I told you that vortices are always in various knots, and unknotting is an important part of turbulent cascade. Unknotting is an important part of the turbulent dynamics. And so like just see this example. If you didn't have temperature change, this is how reconnection will happen. They'll become one vortex. And if you had phase change, it becomes a completely different story. Cold vortices are very different in this context. So like the whole reconnection process in turbulence is messed up. So droplet laden flow, you get like small scale because of baroclinic torque. That's the summary so far. And so like normally when we talk of turbulence, we are putting energy only in the big scale, right? Like the Earth's rotation or some big scale is putting energy. Whereas in clouds, like there's energy coming from here also due to buoyancy. You effectively have chemical energy of these droplets, which go through a phase change, which then put potential energy in terms of density differences, which then gives rise to kinetic energy. So it's a conversion of energy from one type to another. And now, this is one thing which you don't need to understand this graph, but there's only one thing I'd like to tell. We did this back of the envelope calculation in 2022, that's 3 years ago. And what we showed is that unless you have like extremely small vortices, you cannot get rain. So we estimated what it needs to make rain, and with some simple calculations based on vortex evacuation, some basic arguments, we showed, you can say, that only the very tiny vortices are needed, and they are like they're going to happen only at extremely high Reynolds number, so otherwise you will not get rain. Now, happily, our work since then has showed that this back of the envelope calculation is missing something. It's missing some very basic physics. So we need to revisit like how to calculate it. And we're actually able to get rain a little more easily. So how does this, and now we've shown everything in 2D. Does it work in 3D? That's the question which Nikita and Bipin were trying to answer. So then like this is the same photo, turbulence gives centrifugation, blah, blah, blah. We've been through this cycle, and baroclinic torque, the tiny vortices give rise to even more centrifugation. So this cycle makes it more and more powerful. And we calculated that our time scale is in the right range for these droplets that we're considering. And these are the simulations we performed in a 3D box, which is a very small box, only this much. I told you the problems with that. And we are in decaying turbulence, which is also a problem because outside air will keep pushing the cloud, and we haven't done that. And we've taken some 50 million droplets, which is normal. And we've done it in one-way coupling, namely the droplets don't interact and so on. And remember that these are toy, I've written these are toy simulations, and to go to real Reynolds numbers, you need AI. So whatever we gain from the toy simulations, we have to see whether it's true in the cloud or not. We talked about this quantity Q before, and in decaying turbulence, we're starting with some places where it's negative. So at time equal to 0, there's strain regions where Q is less than 0, and vortical regions where Q is greater than 0. And these are the Qs where the particles are. The particles are all in strain regions. Usually they run quickly into strain regions, like they leave the vortices. And by time 16 or 20 seconds, the whole turbulence has decayed. So our complete simulation is only for about 10 seconds. So we are in very fast decaying turbulence. Now, is it cold inside the vortices? Like, is our argument correct? And we see that yes, our arguments are correct, because here's the deviation from the mean temperature, and here is the deviation where the grid points are greater than 0 and those are colder. Agreed? The temperature is lower there, and it's very, very small change in temperature, like this is in degrees centigrade. So it's a very small effect on the mean, but locally it can be a big effect. So the vortices are colder, the strain regions are warmer, the blue, and wherever there are particles, it's very warm. Wherever the droplets are, it's very warm because that's where condensation took place. So like in our, at least in our baby simulation, we're able to show that all these arguments or these hypotheses are actually working out by a small temperature change. Whether it's big enough or not, more work is needed. And then we did correlations of vorticity, the Q quantity, with temperature. So like if the correlations are negative, so inside the vortex, Q is greater than 0, but temperature is less than 0 because it's colder. So it has to be negatively correlated. Outside, Q is less than 0, temperature is greater than 0. So again, they have to be negatively correlated. So we asked this question that is that true everywhere? And yes, like inside the thing, it's negatively correlated inside vortices, and outside vortices, it's negatively correlated. Remember, that's the 0, but much less, because the outside is like, very, not very thick in particles, so the correlations are lower. And this is like the average. So everywhere, this is negatively correlated. So it's colder inside vortices and warmer outside. And we said that because the droplets have left, there's no cloud condensation nuclei inside. So the vortices have to be wet. So we are, looking at the correlation between the vorticity Q and the Okubo-Weiss parameter actually, and the water vapor content. And we see that those are positively correlated. So where Q is less than 0, right, this Q is less than 0, QV also has to be less than average. So that has to be positively correlated, and the other way around. So everywhere you see the effect is bigger in the vortices and less outside, but the direction is the same as it should be. And this is like a photo of normal turbulence, and it's not a very clear photo, but you can see that there are many more small scales formed here, whereas there are only big scales. So that's the message that this is giving. And this is the turbulence spectrum. So for people who know turbulence, like it's versus the wave number, we're plotting the spectrum. And as time proceeds, you will see that these small scale vortices, K being large, they're becoming much more and more and more. After 0.2 seconds already you see something, but after 10 seconds, when our simulation is over, you see lots and lots of scales. So these are all like not very small scale. These are much bigger than a millimeter. So like that's why our back of the envelope estimations were wrong. Like we're getting like powerful vortices even in big scales. So like we don't need very small ones. We're getting reasonably big ones also. They're still not big, okay? First of all, these scales are all very small, like millimeter size. And remember, this is like 10 to the -4, -7. So it went up from -16 to -4, which is brilliant, but it's still rare. So these are the things.
Vortices with water, liquid water inside. How is it possible? You said that it normally centrifuges outside.
Yeah.
Yeah, but how?
I said liquid water is outside.
In the previous slide, there is where Q and T are positively correlated. What was the?
That was water vapor, not liquid water. We're looking at water vapor because once the condensation has happened, the water vapor will become less. Okay. It will become drier. Got it? Okay, the second story is inertia, which I'll go through quickly. Basically, like we can estimate, and this was, I told you, the wrong calculation. We got some minimum Reynolds number for rain, which was like around 1 million based on how it evacuates and things. So we clearly don't have the complete story. Somebody should look at the simulations and make a better story. And yeah, this also has the same idea that, there'll be more small scales. And there's lots of things we've neglected. I'll just mention one thing here, which is that, actually these droplets, as they grow, they can release vorticity without, interacting, colliding, phase changing, nothing. They'll just release vorticity. We've not taken that. We've taken these droplets to be too small to do anything like that. And so they'll also talk to each other. They'll be in four-way coupling. They'll talk to the flow. They'll talk to each other. All that we've neglected. We're studying all that in our group, but I can't talk about it today. And then I'll just show you some examples to show that it's interesting. I have like 5 more minutes, no? I started 10 minutes late, no? Okay. So then that's without the questions, right? So then like Harshit has been doing this very nice work where, if there are two droplets, they will start drifting in this direction. Each droplet by itself, when there's gravity, should only fall down, right? Nothing else should happen. It's so much heavier than air and it should be falling down under gravity. But when there are two of them, they interact with each other to drift. And suppose you have an ellipsoidal shape, like ice crystals and all can be any shape. And even droplets, when they grow, can be all kinds of shapes. They won't be spherical. So then, like, if you, and usually the departure from sphericity by, like, the people who look at those things, they model everything as an ellipsoid. And then they get this drifting. And we are going to say that ellipsoids are a very, very bad thing to model them as. Like, each droplet has to be modeled in whatever way it is and each ice particle. So ellipsoids have 3 planes of symmetry, right? Like if I cut this way, this and that are the same. If I cut this way, this and that are the same, and so on. We're removing just one more symmetry. And effectively, we're making like a kaju shape, which is slapped down. And this is just one such object, which is just tiny object falling under gravity, just to show you that it can do interesting things. So instead of falling vertically, this is what it does. We're just releasing it, nothing else. Because rotation and translation are coupled. So we call it a flutterer.
Here the Y motion is blocked.
We are just moving with the particle. We're moving with the particle. So this is the kind of thing that shape can do. So like we have to remember so many things, like just modeling them as droplets, which are spherical, is bad news, stuff like that. And now if you have 3 spheres, they can talk to each other. So this one will just fall vertically down, this one will drift. If there are 3, then this one will be pulled down by those 2, and then these 2 will come closer. So if there are more than 2 droplets, you'll have clustering. And that itself can give rise to more chances for collision, right? So just these interparticle interactions can be interesting. The reference is this, but this movie is made in the lab by Rahul. These are Rahul Chajwa. These are actual spheres released in an actual lab. And he's done many more things like that. So this is the summary that we talked about. I don't need to repeat it. And this is the story 1 that we talked about. This is the story 2 that we talked about. So we saw like, and these are all our hypotheses or what we feel, and whether they're true or not in real turbulence and real clouds, only the future can tell. And so the conclusion is that cloud computing is calling out for ML methods, and we know what vortices do that can be used. We are slowly understanding what droplets do that can be used. We're slowly, very, very slowly understanding how droplets back react into the vortices. That itself needs to be understood much more. And then we need to understand, like, their own dynamics with each other, with different shapes. Things like that are like very much in the future. We've just done some very basic work, and other groups also have done basic work, but lots and lots and lots needs to be done here. We need to understand interparticle interactions. So can ML incorporate all this without actual computations and feed back to the talk that was given previously, feed back to the big scale and say, now it will rain. As simple as that. Can we answer that question? So thanks for your attention.
Okay, thanks a lot, Rama, for that engaging talk on clouds. So now the floor is open to questions, and you have already asked some questions, but please carry on. We'll go first.
What method did you use for time and space discretization? Are you are using some software to solve this problem?
Yeah, like in the case of the cloud computations, that was Bipin's code. So that thing, it's actually York Schumacher who first started that code, and it basically uses some implicit time stepping, and it uses some spectral method for
But it
space.
is DNS.
It's DNS code.
Next.
Hi, ma'am, I'm Shruti. My question was that you mentioned about the requirement of small vortices. But let's say I have a vortex which is maybe slightly larger in size, but I have a higher temperature inhomogeneity. So my baroclinicity torque in some sense is larger. So in that case also, will the process work? Like, let's say I have small vortex and less temperature homogeneity versus a larger vortex and higher.
So by some chance, if you got a larger vortex, which is way colder, then yes, that physics of, Magnus lift and breaking down, all that will happen. But you can't achieve that in the first place. Like if I have a big vortex, then these droplets will take very long to centrifuge out. So they will never centrifuge out, first thing. And secondly, so before that itself, they'll start condensing. So like the temperature, heat release will be everywhere, inside the vortex, outside the vortex and all. So I need like a short, powerful one, which will eject it so that I get the inhomogeneity. So to create the inhomogeneity, I need the small size. And like we're seeing somehow that we don't need that small size. We still need far smaller, but it wasn't like as exaggerated as the theory.
Ma'am, you have told.
Please introduce yourself.
I'm Swadis Mahabatra. You told about cold vortices and warm vortices. What is the, like, if you are considering like the rotational pattern of like clockwise or anti-clockwise, how it will affect the centrifugation and all those things?
It won't affect. For only the magnitude matters, not the direction of the vortex. So like if it's rotating like this, it will spiral out like this. If it is rotating like that, it will spiral out like that. That's all. So it will do the exact same physics, only with spiraling direction changed.
My name is Deepak. So I want to know like how this small scale vortices, how they are different from the large scale, turbulence which causes planes to rattle. Other than the scale difference, what else is?
So like in turbulence, there are vortices of all scales, all signs, all scales. And one particular scale was shown in that movie where you saw like these rods. But if you take all scales, you'll get a profusion of sizes, you'll get a profusion of vorticities, everything. So it's all like interconnected. Sometimes a big vortex can have many small vortices inside it. So it's not like solid body rotation. There's a lot of interesting things happening where you have large scale vorticity, inside which small scale vorticity is embedded. So like lots of such complications are there. So fundamentally, like if I take a simple vortex, it will behave the same whether it's large or small. Only time scales will be very different in the two. And so like some of them will be effective and some of them not. But in real turbulence, there's much more happening. And every time there's reconnection, you're getting small scale vorticity, you're getting a debris which is thrown out. So like that debris and all will be less in large scales than in small scales. All debris is usually smaller scales, things like that. So yeah, like in other words, if I had a small plane, it can get thrown by a small vortex. Maybe next. Yeah, you can go and then pass the mic.
Good morning. My name is Anirudh. It was very. I just want to know, does polarity accelerate or decelerate this process in the micron scale?
Polarity of what?
Particle polarities. Considering we have aerosol as cloud condensation.
So you're saying if there's some electrical charges on it? No idea. There are people who are doing work like they're trying to understand lightning, they're trying to understand these things. But yeah, it does have some behavior changes, but we don't know. So like there's work going on in IIT Madras in Anubhav Roy's group on this, where, suppose these droplets are attracting, they charge such that they're attracting, then coalescence can be more effective, or if they're repelling, coalescence will be less effective, all of that. So there's lots of things which happen, but we're not, in our kind of work, we're not going that small in scale where they're actually touching each other. We've not looked at the near scale dynamics, but lots is happening and we don't know.
Rama, that was a fascinating talk and fascinating a lot of interesting microphysics that you have unraveled. And I think this is a great deal of new information that might help our better parameterization. And that is the question I think you propose.
Yeah.
My question is, so how do you go about it? Do you have an idea about what kind of training data that you will need and whether that data is already available from your simulations, or you need to run a different model simulations which create a set of data on which some of these physics will be involved, and that will result in the training to derive a parameterization. So I think that should be our goal, and that is in the interest of all our people in the large scale working on improving the predictions. So I think there is a lot of potential about it, but we need to think about what can we do now, because you have addressed a lot of other questions which will never be answered. So we can always go on doing this microphysics for a long time and not answer any of these questions. So we have to, with this additional information, additional knowledge that we have, what do we need to do to translate it to a parameterization? And that is all I can think about is use EIML with a whole set of training data. What is that training data? Can we generate it? To generate that training, what do we need to do?
Okay.
Can you have an idea on that? Sort of talking that.
Okay, so the first thing is that we need to run these codes. So Bipin has a code, Ravichandran in IIT Bombay has a code. In fact, that code, they're trying to make it very, very parallel, very, very powerful by collaborating with people in IASC and making it GPU and so on. So once it becomes like hyper efficient, you can say, the first thing is to run it with bigger and bigger Reynolds numbers, with more realistic aerosol and droplets. We've only done droplets, which is kind of cheating because aerosols won't get centrifuged so much. So like how much of the aerosols have become droplets? So we can go earlier in the process, do that. So we need like many more simulations, first of all, on more powerful computers. They will form the training set. But we have all the physics and all the code. There's nothing else new physics to be done, but only data sets have to be generated. They will form the data set, and you need intelligent AI. You cannot just like blindly train and say, ab karo. We have to now remember the physics, which is, which is that, you know, it's going out of vortices. So like how much is happening in this size and how much is happening in that size? Can I even extrapolate? Or can I not extrapolate? So like if I can extrapolate, how will I do that? So these are the first questions which AI should ask, and it should say, okay, like I want to replace, you know, finally like each vortex is only doing centrifuging. So I shouldn't be computing quadzillion vortices. So can I use that thing that if I have this many small scales, this many big scales, how much centrifugation is happening when? Can I learn that and incorporate it? And then like as the simulation proceeds, I'm creating more and more small scales. So how is that feeding back on the process?
Also, I think we'll need something more because this is on a completely no background. But in the atmosphere, there will be large scale motions affecting these, because collision coalescence will be affected by if there is a downdraft or updraft inside the cloud, right? So that is something that needs to be factored in any of the So how do we do that?
So the only thing we can do is like, you know, have a different forcing. Right now we're having periodic forcing, but we can account for the updraft and downdraft.
That can be done in the simulations.
So basically we'll change the terminal velocity of the droplets. That will be the biggest effect. So instead of falling, they'll be rising if there's an upward convection. So with a different terminal velocity, and if it's different in different places, different things can happen. So we can model that into the simulations. And we need more data sets with that.
What do you think is kind of, can we make a plan that, okay, this can lead to something? What kind of resources are required? What kind of people are required?
We can do that.
I think we should do that. I think it's a very fascinating thing, and we have.
I think we should do that. Otherwise, all this is a waste.
better. Because
Yeah.
Otherwise, somebody will.
Yeah.
The physics people will take time, but doing the AI ML part, if the data
Yeah.
is available, somebody will do it like that. So the question is, and we are sort of we have a lot of original ideas, but we are never getting that into actual applications.
Yeah, we're never
And then
parameterizing on that. Yeah.
So I think we should.
Yeah, I totally
we
agree.
should seriously think about it.
Yeah, we should.
Thank you.
Thank you.
There are a couple of questions from the online participants. So one question from Tukaram Zore, how the latent heat of condensation release during condensation process affects the vorticity and droplet?
So that's basically what I've been talking about. It's the latent heat release, which is making the temperature bigger wherever there's condensation. The reverse also can happen. At the edge of the cloud, you can get evaporation because everything is dry. So you can have ultra latent heat release and things like that. So basically where the droplets are determines where the condensation occurs.
And another question from Moti Gupta, this is more like a comment. Essentially from high level, I have understood there is complex interaction happening inside clouds at smaller scales, while bigger models can't capture it natively. But is there like an average behavior that can explain maybe 60 to 75% of things that is not accurate, but still good enough for course purposes?
We actually should go in that direction because all of these effects are going to be so different if you have a cumulonimbus cloud or if you have a stratus cloud. I mean, it's going to all the what updrafts and things that were talked about, those are going to make a difference, and the size is going to make a difference. How much space do I have inside the cloud? So yeah, we should be able to do this, and that's for the future. And in fact, AI should actually do things like that rather than giving a very exact answer. If it can get a coarse answer correct, that will be great.
Right. So that is the different art system models, like the one which Gokhan talked about and various other models. Currently, do they take care of these cloud microphysics, these droplet dynamics and all these things at all, or
they have some round numbers put for those? So
some coarse parameterization.
Yeah, you'll have a Reynolds number dependent growth rate, or you'll have a probability of rain based on some of these numbers. That's all.
Yeah, these are considered as subgrid processes, I guess.
Yeah, they're all very, 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 very subgrid. These are subgrid even for DNS, and DNS is itself so subgrid. Yeah.
So in all these art system models, Gary, there are what is called microphysics parameterization. In terms of the physics involved here, there are much more sort of limited in terms of scales. So therefore they have their own errors and biases. So what is the idea is that with all this new information or all the new understanding, how can we improve that? I think that is the goal. And some parameterization will have to be there in all these models. We have to have parameters. How do we improve? Because so far, I think the building a parameterization requires understanding the interaction between the very small scale and the larger scale. So how do they interact? How they depend on each other? And that in earlier we could not do that very easily because it is so complex, so non-linear. And now with AI, it gives an opportunity to understand that easily or relatively easily. But if she has to include more of this into the building the parameterization, unless you have the data and then you have to compute it and then generate it online, as he was telling in the first talk, it will take a lot of time, and that's not possible. That's not sort of computationally or economically viable. So what we need is to do something, build a parameterization with some data first, and then use it into the models so that you can have a sort of efficient and more accurate, but more computationally efficient method.
Okay, Roxy, Bipin, Shikha, any of you have any questions? Can unmute yourself and ask. Okay, if not, let's thank Professor Rama Govindarajan for this engaging talk.